All right, the focus today is motion problems. Okay, so we've seen these. This is our object moving back and forth in a straight line. Okay, remember we're not turning any corners. Whatever we see is back and forth. The other thing to remember about these particular questions is the relationship between position, and it may be an S or a D, and velocity. So the derivative of position will be velocity, and the derivative of velocity will be acceleration. And then of course if we take the antiderivative we can go back the other way. Okay, so remember just that relationship, and please when you're looking at these motion questions don't forget some of the physics knowledge that you all have. We've talked about it in class. The area under a velocity time graph is the distance traveled and the displacement, so keep all that in mind as you go through these questions. All right, in the first question, we've seen this now a couple of times where they've given us a graph and a chart. So we have the graph of velocity time in feet per second of a car traveling on a straight road from 0 to 50 seconds. A table of values for velocity at 5-second intervals is shown on the right. So we also have the table of values for these particular things. During what time intervals of time, or what intervals of time is the acceleration of the car positive, and give reasons for your answer. And then we're going to find the average acceleration of the car over that interval. All right, so for part A, the thing to remember here is that acceleration is the derivative of velocity, and the derivative is slope. So this question is really just asking us, when is the slope of this curve that we see here positive? When is that slope positive? Well, if we look at all of this, it seems to be positive all the way up to this point, which is 35 seconds. Then it becomes negative, and then it's positive again this last jump here from 45 to 50. So I'm just going to say we are from 0 to 35, and we can say 45 to 50. I'm not going to include the endpoints because that could be a zero, probably a 0 at both of these parts here, and we don't know what really was happening before or after this, so I'm not going to include them. Another way to do this, you could just say 0 t 35 and 45 t 50. So you could do any of those. All right, let's find the average acceleration of the car, and they're actually giving us the units here in feet per second squared over this interval. We want the average acceleration. Well, the average acceleration is really just that line, the slope of that line. Okay, so we got a couple of ways to do it. We can do it here. We could also look at it with our chart as well. But we want the average acceleration, so it's the slope of that line. I'm just going to slide some things up here for us. Okay, so if I want to find the average acceleration, I'm going to take rise over run. It kind of looks like this. I want the velocity at 50 minus the velocity at 0, and then I'm going to divide it by time. So this is the change in velocity divided by the time. Now from 0 to 50, that's just going to be 50. All right, so I'm going to the chart, maybe a little easier to read than off the graph. So the chart says at 50 we're at 72, and at 0 we're at 0. And that whole thing is divided by 50. So if I punch that into my calculator, 72 divided by 50, I'm going to get 1.44, and they gave us the units, but don't forget to put them here as well. I'm going to say feet per second squared. So there's our average acceleration. Now we could get that same place if we back this up. Average acceleration, we've been doing these sort of things. If we went 0 to 50 of our acceleration, that could be our average acceleration, kind of the integral notation. I should put a dt in here. But the integral, the antiderivative of a is the v. So that does become like v final minus v initial, top minus bottom. And then this is what we have there. So it does work algebraically, or really just find the slope of the line. Rise over run. All right, that question continues then in part C. Find one approximation for the acceleration of the car at time equal to 40. So we want the instantaneous acceleration at time equal to 40. So time equal to 40 is this point right in here. So it wants one approximation. There's a number that we could use here. Okay, so to start with, we could find the tangent slope right here. Now that may be a little harder, but if you sketch one on, we could use these endpoints and we could find an approximate slope of that tangent line. So we could do it that way. And it looks like 35 and 90 and 50 and 50. And if we did that, we can get an approximate acceleration of the car. So let's try that one, the acceleration at 40. I'm going to take that as, again, think of it as rise over run. What are we doing here? So we started with 50 minus, we started at 90. And I'm going to divide that by, we ended at 50, and we started at 35. So if I go ahead and punch that into my calculator, I'm going to get negative 2.67. So that would be one way in feet per second squared. Now, there are a number of different ways using the chart as well. We want the acceleration at 40. So it's still slope, but we could do between 35 and 40. So we could use those two numbers and find the slope of that line. So the slope is always still kind of rise over run. Okay, this becomes my rise. So it's going to be 75 minus 81 over 40 minus 35. So I could punch that in and I can get another approximation. So I have negative 6 divided by 5, negative 1.2. The fact that it's quite different from the first one doesn't matter. It is one approximation. Okay, let's keep going. What is another one we could use? And you only need to do one, but I'm just showing you all the different ones that we could use. As long as 40 is in it, we could do 40 to 45. So I could have taken, now it's getting a little messy in there, so let's just clear some of that stuff out. Oop. Getting a little messy there, and it's not letting me erase this, unfortunately. Okay, so I can still see them. We got 60 and 75, and we went from 45 to 40, so that's what we have there. So again, this becomes minus 15 divided by 5, so there's a negative 3. So again, quite different from the others. Maybe close to that first one, but we don't know. Another way, and probably the one that I go to most, if I want 40, I'm going to let 40 be the midpoint of my interval, and I'm going to go from 35 to 45. So one final way we could have done this is 45 or 35 to 45. So we ended up at 60, we started at 81, and we went from 35 to 45. So we ended up at 45, started at 35. This is all kind of final minus initial. Final minus initial. That's all we've done there. And we get 21 divided by 10. Okay, I don't know why I wasted time punching that in. That is 2.1 feet per second squared. any one of those would work. Just make sure you show your work for whichever one. Now, this year, it's going to be, a little different. You're still writing it out, though, okay? Take your picture, send it in, however they're going to have you do it. But just show one of those. All right, finally with number 2. So now I am going to get rid of all of this stuff, clear up some room for us. Okay, so D says approximate 0 to 50 of VT dt with a Riemann sum. Okay, so we want to do a Riemann sum of midpoints and 5 subintervals of equal length. Okay, so now unfortunately I did mess up my picture there, erasing everything, so I got to bring that back. So just give me a minute and I'll go get that. Alright, I got my chart back here. So we want 0 to 50 with Riemann sums. They are midpoint Riemann sums, so they're midpoints and 5 subintervals. So I'm looking at 0 to 10, and 5 is going to be my midpoint. 10 to 20, 20 to 30, 30 to 40, and 40 to 50. So there's going to be my 5. Now, that means I'm going to write this out, 0 to 50 of VT dt. So you can see our motion question, it's still going to involve a lot of the other stuff, right? You're solving a Riemann sum. So the first one has a base of 10, that was my interval, and the midpoint is 12. Plus the next one, base of 10, my midpoint now at 15 is 30. And then I have 10. My midpoint at 25 is 70. Okay, 10. My midpoint here is 81. And I'm going to squeeze this one down in here. I need one more 10, and that midpoint at 45 is 60. So I'm going to punch all of that into my calculator, and I get 2,530. Now it says, using correct units, explain the meaning of this integral. So if I did all of this, remember I'm taking feet per second times seconds. So I'm going to end up with feet, which is the total distance traveled. And I can say distance here because it was all in the positive direction. Okay, he did slow down for a little bit, but it was all in the positive direction. If you said total displacement, that's going to work as well. Alright, here we have a particle moving along the y-axis, and they give us the velocity of the particle. The fact that it's on the y-axis doesn't matter. That just means it's moving up and down. It's really not going to change our work at all. Just remember that we're only moving in straight lines. So the fact that it's moving up and down makes no difference from moving left and right. And don't worry about, oh, it's up and down, I got to factor in a gravity or anything. That's all taken care of by the formula. They gave us the formula for velocity. So let's go ahead and start answering some of these questions. It says, in which direction, up or down, is the particle moving at time equal to 1.5? And they want to know why we know that, okay? So to find the direction, let's just look at what its velocity is. So I'm going to really just find, v at 1.5. So I'm going to plug that in, 1.5 sine 1.5 squared. Now you can do this on your calculator, or you could enter the formula here into my calculator. So in fact, I'm going to go into my calculator and I'm going to put in x sine x squared just into my graphing calculator and graph it. Then I can go to second function, calculate, and that's where we find all our stuff. And I'm going to do number 1, I'm going to do a value. And if I punch in 1.5, I'm going to go second function, calculate value. If I go 1.5, I get y is 1.167. And because it's positive, that means it's moving up. So I'm going to say v is positive. Therefore, the particle is moving up. Okay, and we've answered A. Okay. Let's keep going with this one. Find the acceleration of the particle at time equal to 1.5. We want the acceleration of the particle. Okay, so let me just take care of some of this stuff here. Let's get rid of all of that. And let's do part B. What is the acceleration of our particle? Well, acceleration is the derivative of velocity. So we got a couple of ways to do this here. So we have the velocity formula, so we could go through the product rule here. It's really just product rule and chain rule, and I could find what the derivative is. Now they may have us do this, because I'm going to show you a really fast way that I don't need to actually find the derivative. I can do it on my calculator. But if they ask what is the derivative of v, we're taking the derivative of the first, so the derivative of t is just 1, times the second, there's t squared, plus the first times the derivative of the second. The derivative of sine, remember we did this little deal, the derivative of sine is cosine t squared. There's some chain rule here. I have to multiply by the derivative of the inside. So we got a little bit of chain rule in this second piece here. So that's what we have. I'm going to rewrite one more time. I don't want the 1, so I'm just going to go sine t squared plus, I'm going to multiply those two. That's 2t squared cosine t squared. And let's put those brackets over here as well. So now that I have the derivative, or the acceleration, it's just a matter of putting in 1.5 into all of these spots. Now, a very quick way to do that, if they do not ask what the derivative is, and they just want to know the acceleration at that time, on my calculator, second function, calculate. Right? If we go all the way down to number 6, you can see dy dx. That's the derivative. That's the derivative. So I'm going to go to number 6, second function calculate, and I'm going down to number 6, and then I'm going to punch in x equals 1.5. Now, just be careful when you're reading this. I'm actually maybe going to show you an image of the calculator in a minute here, but the answer is actually up above the x and y's. So when I go second function calculate and I punch in my 1.5, I got to make sure I read the derivative. Either way, when I take the derivative using the formula or using my calculator, I'm going to get negative 2.049. Now the question becomes, is the velocity of the particle increasing at 1.5, and why or why not? So I'm just going to slide this up so I can write down my information here. I'm going to say that my acceleration is negative. It's negative 2.09. But the velocity, if you look at your graph on your calculator, the velocity at 1.5, and even our answer from part A, was positive. So if my acceleration and velocity are in different signs, that means we're slowing down. We're slowing down. So the question said, is it increasing? We got to say no. We're going to say the particles speed is not increasing because acceleration and velocity are in different directions. So something along those lines. Make a statement to show that you understand what's going on here, right? And honestly, this first part may be enough. If you say acceleration is negative, velocity is positive, so it's slowing down, that could be enough here. I'm not sure what how picky they're going to be at that point. Okay? All right, so now, unfortunately, I'm just going to get rid of a few of these things so we can look at the next questions. So let's... All right, given that yt is the position of the particle at time t and that y0 is 3, we want to find y2. So again, this could be, I'm looking at this one, and it may have been set up as a non-calculator type question because they're asking us to find y and then with the boundary conditions figure out what c is going to be. So we have yt, the position of our particle, let's try that again, yt is the integral of vt. So that's what they're saying. So we need to find the antiderivative of vt and then go ahead and put in our conditions and then find y2. So I'll show you that pretty quickly to find the integral if we didn't use a calculator. And then once again, I'm going to show you a calculator way that's going to get you to the same spot. Now, unfortunately, with this part here, we have some chain rule and product rule. We got to use some u substitution. So I'm going to let u equal my inside function t squared. That means du is going to be 2t dt. But I don't have 2t, I only have 1t, so it's going to actually be something like this, like 1/2 du. So let's do a little swap here. And this now becomes the integral. That t and the dt becomes 1/2 du. And sine of t squared becomes sine of u. I'm going to move the 1/2 to the outside, so it's still there. Take the integral of sine of u. Well, the integral of sine, now we're going this way, antiderivative, is negative cosine. So let's be careful here. It's a negative cosine of u. I'm going to swap right away and say that's t squared. And then we got the plus c. So I get negative 1/2 cosine t squared plus c. That is yt. Now at this point here, I'm going to need to use my information. We're told y of 0 is 3, so let's plug that in and figure out what c is going to be. I'm going to change colors here. So if I know y of 0 is 3, cosine 0 squared is just going to be 0. And we're going to find c. Well, cosine of 0 is 1. 1/2 times 1 is negative 1/2. Plus c is 3. We can get c is 3.5. So now I have yt. The position is negative 1/2 cosine t squared plus 3.5. And we're going to punch in y of 2 is what we want. So just type that into your calculator. When I do that, I'm going to end up with 3.827. And that is the position at time equal to 2. Now, that was a non-calculator kind of work here. Now, they can get around it, giving us a harder equation or something else, but so that we have to be able to use our calculator. Here's another way we can do this on our calculator. Okay, so sorry about that. I'm going to put y2 is like the integral from 0 to 2 of vt dt. So that's what we're going to look at. Where is it? And basically, the displacement of the particle. And then we got to do a little bit more because we're told that time 0 is already at 3. So we're going to add 3 to that. And if I do that, this is the displacement of the particle over that time interval from 0 to 2, and then where was it at 3 when it started. If you do that whole thing, you're still going to end up at 3.827. Okay, finally, let's wrap this up. I got to bring back my question here now. Let's get rid of a bunch of that. Come all the way down here. Okay, I'm going to... Part D, find the total distance traveled by the particle. Well, you can't see it. Hopefully you had your calculator going, but if you look at your calculator, the graph of our particle does something along these lines. It goes up in here, and then it crosses over, and then it gets into this part here. From 0 to 2, it does cross over, and it goes below. So displacement is all of this, but our work on velocity time graphs knows that at this point here, it turned around. If we just want the total distance traveled, we don't want this to be a negative. So we can get around that, again, on our calculator. If I go to y equals, and I put in the absolute value of our function. If I put in the absolute value, then the graph is going to turn that over. So it's going to have this little bit here, and then instead of going underneath, it's going to turn that over. And it's going to take all of that, and now we're going to get this sort of deal going on. And when it goes to 2, it'll get all of that. We're going to find the integral. So second function, calculate. Number 7, you can find the integral from 0 to 2. When you do that, second function, calculate. Number 7, 0 to 2. I still get, sorry, I did not do this. Okay, when we do that, we get 1.772. So that is the distance that it traveled during that interval. Okay, don't confuse part C and part D together. Part C is just where it is. What was the distance traveled? It went 1.772 units over this interval. All right, try the questions, and we'll keep going, getting prepared for May 12th.